All right. So again, finding the directional derivative and the directional angle theta from the positive x-axis like that. This is not the same function. At the point P here. So we're given this function, I'll take in that direction. If the direction angle is 7 pi over 4, then the unit vector is cosine 7 pi over 4, sine 7 pi over 4 is this one.
Isn't 7 pi over 4 in the other quadrant though? Isn't it in the fourth one?
Oh golly, I drew it in the wrong quadrant. I was thinking 3 pi over 4. Yeah, thank you. Jeez. Just testing you, of course. Yeah. 7 pi over 4. And so now I've got these coordinates. Yeah, square root of 2 over 2 and square root of 2 over 2. And the coordinates are square root of 2 over 2 minus square root of 2 over 2 by the unit circle. And that makes those the components of the vector. So the minus is on the wrong one. There we go. Now, to compute the directional derivative, I also need the gradient, right? So I'll take the gradient of this function. That means I need the partial derivatives of this, right? The gradient is df dx I plus df dy j. It's just a vector of partial derivatives, right? In order. Partial of this function, you have to use the chain rule. You let u equal 2x plus y. And say partial with respect to x is derivative of f with respect to u, ordinary derivative actually, since that's one function of one variable, df du dx, that multiplies I plus df du, du dy times j. Well, partial of tangent is secant squared. The derivative of tangent is secant squared, so I get secant squared u, and then du dx, if u is 2x plus y, is just 2. So it's secant squared u times 2 I plus derivative of tangent again is secant squared. Derivative of u with respect to y is just 1, right? And then times j. Well, u is 2x plus y. And at the point in question, x is pi over 6, y is pi over 3. So this is twice pi over 6 plus pi over 3 is 2 pi over 3. So what we're going to do is take secant squared 2 pi over 3 times 2 I plus secant squared 2 pi over 3 times j. And there is the gradient at the point. I say this is the gradient here. Now we want the gradient of f at the point pi over 6 pi over 3. Now let's see. We can go back to the unit circle again. This is a trigonometry problem, isn't it? So that comes over here. There's 2 pi over 3. I drop the perpendicular, I get sides 1/2 and square root of 3 over 2 out of trigonometry. So the cosine is 1/2.
Excuse me.
Yeah.
When you find the partial derivative with respect to y, should it not be 1? I don't know.
Yeah, it is 1. Yeah, I'm saying df du du dy du dy is equal to 1. Partial of f with respect to y, however, is secant squared times 1. So if I say partial derivative this with respect to y is derivative of tangent is secant squared times derivative of 2x plus y is 1. Right? So I think that's okay. Over here I have cosine of 2 pi over 3 is minus 1/2, just off the unit circle. So secant ought to be minus 2, right? It's reciprocal. And the secant squared ought to be 4. So this ought to be 2 times 4 is 8i plus 4j. All right, so there's the gradient of the point. Here's the direction vector, and now I better move the camera over. And the directional derivative is over duf at the point, pi over 6, pi over 3, is the gradient at that point. Let's just write it short. Gradient of f dot u. That's how we have the directional derivative. The gradient was 8i plus 4j. The unit vector was square root 2 over 2i minus square root 2 over 2j. So it looks like we have 4 square root 2 here minus 2 square root 2 here. This times this plus this times this is this 2 square root 2 looks like. Hopefully that's the answer in the back.
Can you go over like the visualization part of that a little more?
Yeah. I wish I could draw this function. It's not easy to draw that one. So I just drew a generic one here. See if I can draw it bigger. I'll put it over here in fact. What am I doing? Visualizations, you have some surface up here. Z equals f of x, y. The directional derivative says, suppose you have some point x, y in the xy plane, or you can label it x, y, 0 if you want. You go up here and I say, I want the slope of the tangent line that's in this direction within the xy plane, right? At some angle theta from the positive x direction, theta. And so you compute the components of this vector, and they're just cosine theta, sine theta. That's your unit vector u. And then you want to find the slope of the tangent line in that direction. This is what we call the directional derivative of f at u. And then plug in this point here. So I could call this point x0, y0 or something like that. And this would be the directional derivative at x0, y0. And the way we compute it is just this. We say directional derivative is gradient of f dot u. So we compute the gradient dot product with the vector cosine theta, sine theta. Make sure you use a unit vector when you compute the directional derivative. Is that better? Is it a little easier to see, I hope? That is, it's in a tangent. It's in a plane that goes in this direction. You find the slope of the tangent line within that plane.
So the tangent line is on the, like the figure you drew above.
Oh, yeah, that's a good question. Actually, the tangent plane, it's funny that you're leading into tonight's lecture. I've got to talk about tangent planes. I mentioned before that really what you're doing is finding the tangent plane, and this is the slope within the tangent plane. What we're going to do tonight is say there is a vector perpendicular to the surface here, and we call it the normal vector n. And then there's a plane perpendicular to that we call the tangent plane. And every curve that you take within this surface will be tangent to a line within this plane. And the idea is, if we want the slope of the tangent line in this direction, it's actually the slope of this line within the tangent plane. And that's what happens here is the gradient points in the direction of steepest descent up this tangent plane. So this would be the gradient of f. is in the plane actually down here, not up here. It points in this direction. And then when you take the gradient and dot it with the directional derivative, then it gives you this slope here. Okay, anything else we should look at? Move this over a little more then. Oops. Well, the main topic tonight then is tangent planes and normal lines. So the next section. You've seen planes before. Recall from calculus 3, the tangent plane, not the tangent plane, the plane with normal, a perpendicular vector, n equals a, b, c of its components, and point on the plane, x naught, y naught, z naught, has a point normal equation. A times x minus x0, x naught plus b times y minus y naught, plus c times z minus z naught equals 0. It's not too hard to derive that actually. But that's the point normal form for the plane. And then if you multiply this out, this shows that every plane can be put in the form ax plus by plus cz equals d. Now, what about the tangent plane? If f has continuous partial derivatives, meaning actually in a region about the point. And P with coordinates x naught, y naught, z naught is a point on a surface given by f of x, y, z equals a constant. Then the normal, n equals the gradient of f at P is the normal vector. It's just defined this way for a good reason. And what immediately is a normal line? This is capital F, just to follow the notation, sorry. Well, you have a vector, n, and a point. If we say this is ABC. But actually, let's, this is the vector df, dx, df, dy, df, dz. That's how the gradient is defined, capital F. all evaluated at the point. It's obvious you have a point and you have a normal vector. So you just, by equation 1 here, let's give it a number. You have this tangent plane, df dx times x minus x naught, capital F, plus df dy times y minus y naught, plus df dz times z minus z naught equals 0 is the tangent plane. Furthermore, you can get the normal line. How do you get a normal line? It's pretty easy too. All right, if you're given a point and a normal vector to the plane, you use point normal form for the plane, equation 1. Also, since you recall parametric line, given a point and a direction vector, is just, wow. I don't remember if these parametric equations are ordinary ones now, or the vector. But x equals x0 plus at, y equals y0 plus bt, and z equals z0 plus ct are the parametric equations. I'll just put both of them. Or r of t equals the point is a vector with coordinates with components to the point plus t times the normal vector is the normal line. So this will put it in vector parametric form. This will write parametric equations. So there's the normal line. But it all just goes down to those definitions or those ways we did planes and lines before. A line can be written given a point, x naught, y naught, z naught, and a direction vector ABC. This immediately was the equations for the line, and I should put what A, B, and C are here. I'm sorry. So this would be gradient of f times t. I'm sorry. Partial of f with respect to x times t plus partial of y, partial with respect to y times t plus partial with respect to z times t. The components of the gradient. And these are all to be taken at the point. So all it is taking your equations from before for writing a line. If you have a point and you have a direction vector, you write down these equations immediately. X0 plus AT, Y0 plus BT, Z0 plus CT. Just do it now, but the direction is the gradient. Or you can write it in vector parametric form. A vector to the point plus t times the direction vector. This was just your ABC before. It's the same thing as before. You just replace ABC again with the vector partial derivative. So it's just replacing ABC with the 3 partial derivatives, and you get the tangent plane, we can call that 2, and the normal line 3. Let's look at a problem on that. Okay. So I have this one. Suppose I had x squared y minus 4z squared equals 7. And I have a point minus 3, 1, minus 2. Is on the surface.
Can you move the camera?
Yeah, thank you. So here's the surface. Here's a point on the surface. And suppose we said find the tangent plane and the normal line. It all goes back to find the equation of a plane. You write the point normal form using the point in the normal vector. Find parametric equations of a line, you use a point and a direction vector. Write these down. So find the tangent plane. Equation 2. Well, you take the gradient to find the normal vector, and that's the only difference from what you did before. So this is f of x, y, z equals a constant. Right? As specified in the theorem. This is a polynomial 3 variables, so it's got derivatives of all orders. So we just compute that the gradient of f is, what's partial with respect to x, we could say it's 2xy, right? What's partial with respect to y, we could say, oh, it's x squared. What's partial with respect to z? Oh, it's minus 8z. So there's the gradient. But what we need is actually the gradient at this point. Assuming this is a point on the surface, we just plug it in, minus 3, 1, minus 2, and we'll get this for the gradient at that point. 2 times minus 3 is minus 6, times 1 is still minus 6. Then x squared is 9, minus 8z would be 16. So there's the gradient vector. And now you just write down your equation for the plane but from before, right? Say here's your coordinates of the point. Here's your A, B, C. You just write down the equation of the plane. A is minus 6 times x minus x naught. Plus B is 9 times y minus y naught. Plus C is 16 times z minus z naught. Z minus a negative 2. All equals 0. Same plane equations before, you put in the gradient for the A, B, and C. So this is minus 6x plus 9y plus 16z. And then let's see, minus 18 minus 9 is minus 27 plus 32 gives 5. So this would be an okay answer. Or some people like to put the minus 5 on this side of the equation. I do actually. But here's the equation of the tangent plane. Exactly the same thing you did before. A times x minus x0 plus b times y minus y0 plus c times z minus z0. That's equation 2. Equals 0. Or a, b, and c are just the partial derivatives of the gradient. All right, so that's the first type, and I give you 2 of those for the homework. The second type is, well, not every surface is given as f of x, y, z equals a constant. What if we have this special case that comes up quite a lot of the time, where we just write z equals f of x, y. Now, how do we find the tangent plane when it's given in this form? Well, obviously, we can put it in that form, right? So we just rewrite it equivalently as z minus f of x, y equals 0. This is a little f on this one. So they're using a capital F when they have the surface is defined by capital F equals a constant. They're using a little f when it's this other case, z equals a function of just x and y. So we'll rewrite it in this form, and now we're going to think that this is f in the last theorem. So by our last, actually definition technically, we should call it a theorem. By our last definition, we say we have gradient of f times x, partial with respect to x times x minus x naught plus partial of f with respect to y times y minus y naught plus partial with respect to z, and all these have to be, partial derivatives have to be evaluated at the point. Times z minus z naught equals 0 is the equation of the plane. Again, it's what you saw before, replacing ABC with partial derivatives. But now this capital F is z minus the little f. So partial of this with respect to x is 0 minus partial of little f with respect to x. Partial with respect to y is 0 minus partial of little f with respect to y. Partial with respect to z is 1. And now we get this. Z naught, what is that? We can now make a nice substitution. We can say Z naught is actually f of x naught y naught, right, by the equation that we're given. And when we put that all together, we get this. Minus, let's add these over to the other side, and we get z equals f of x naught y naught. That's adding minus f of x naught y naught over there. Plus this one over here, at minus this one over here gives plus df dx at the point times x minus x naught. Plus, because we're subtracting this one over, df dy times y minus y naught. And we can write it in that form by adding all but the z over to the right-hand side. And there is the equation of the tangent plane for the special case. Oops. Got moved it too far to see that. You still need that. It's hard to tell if it's in the right spot. I think that'll work. So that is a theorem, if you like. That for the special case that comes up all the time, z equals f of x, y, having continuous partials. That was a hypothesis of the first theorem, so we have to carry this over. Continuous first partial derivatives, that is. The equation of the tangent plane 2 becomes this one, which I guess we can call 4. C equals f of x naught y naught plus df dx at x naught y naught times x minus x naught plus df dy at the point times x minus x naught, y minus y naught. And at this point, I want to emphasize that it's taken at the point, so we can put something like this, a little bar down here and say this means evaluated at the point. There's the equation for the most common tangent plane case. I have trouble memorizing this stuff if I don't tie it in with something. I hope this will help you. I'm going to say, note the similarity to when we were given y equals f of x, and we wanted the tangent line. What was the equation of the tangent line? Anybody remember that? This one comes up so often, maybe some of you haven't memorized. What's the equation of a tangent line just immediately by memorization out of y equals f of x? Well, it's f of x0 plus the f dx taken at x0 times x minus x0. Remember seeing that? It's also called the local linearization. So you can look up in your textbook and find the local linearization, then they'll say L of x equals this. Or they'll say, what's the equation of the tangent line? And this is it. And how do you know that's the tangent line? I mean, you can do exactly the same kind of derivation we did here, or you can think simpler and just say, well, if I plug in x0, then x0 minus x0 is 0, and this goes away, I get f of x0. So it goes through the point, x0, f of x0, because I can plug in x0 and see that, right? This is a minus here, I don't know if that's clear. Then, what's the slope of this thing? If I take the derivative, this is a constant, it goes away. Derivative of x0 times this is a constant, goes away. I just get derivative 1 times df dx. So this is a function whose derivative, if you just take the derivative and plug in x naught, derivative of x naught is df dx, the slope of the function, and it goes through the point. You see that by plugging in. And it's a line because it's a number plus a number plus a number times x. It's y equals mx plus b. It's what we call the tangent line, right? It's a line. It's y equals mx plus b. Goes through the right point, has the right slope. That's it. So you can do it that way, or you can do a derivation like this, it turns out. And then you compare this and say the tangent plane is really just the tangent line that I memorized with one more term, right? And I have to use partial derivatives, right? Z instead of y is the function of the point plus the derivative times x minus x0 plus one more term, derivative times y minus y0, and you have to use partial derivatives here because it's a function of two variables. But that's the way I memorized that. I had trouble remembering this stuff. Thought, oh yeah, it's just like the one I memorized. One more term. So let's try a problem on that now. The special case. Suppose I have z equals square root of x plus square root of y. Find the tangent plane at the point 495. And I'm going to change the problem from the book and just say it's 0.49, because the nice thing about this special case is you only have to have the xy coordinates, and you can just plug them in to find the z coordinate, right? So we'll say here, this is x naught and y naught. So I have, and this is f, little f this time. So f of x naught, y naught is f of 49, is square root of 4 plus square root of 9. That is 5. Then I have df dx that I need for formula 4 is 1/2 x to the minus 1/2. So df dx at the point in question, 49, let's put it the other notation, 49 is 1/2 square root 4 is 1/4. Then df dy, just by taking the partial derivative, is 1/2 y to the minus 1/2 is 1/2 square root y. So df dy at the point of tangency 4, 9 is 1/2 square root 9 is 1/6. Now I have everything I need. You put these in the 4, and we have the tangent plane. Z equals the function 5 plus the partial with respect to x 1/4 times x minus x naught is 4 plus partial with respect to y, if you're looking at 4 as 1/6 multiplies y minus y naught, or y naught is 9. There is the equation of the tangent plane. What you really like to do for these is simplify them, right? You can multiply this out in group-like terms. You get z equals 1/4 x plus 1/6 y plus 5 minus 1 makes 4 minus 3 halves makes minus 5 halves. So it looks like that. There's the equation of the tangent plane. Well, you should always see, remember the equation, but the standard equation for a plane is ax plus by plus cz equals d, right? An arbitrary linear equation in 3 variables with a, b, c, not all 0 is always a plane. Every plane can be put in this form. So you notice if you carry these over, it's an ax plus by plus cz equals d. This is always a plane. Comments or questions on that one? All right, then the normal.
How did you get 1/2 times the square root of 6 equals 1/6?
Oh, I wrote 6 instead of 9. I was thinking 6 over here. I'm sorry. I was plugging in the 0.49. It's 1/2 square root y is 1/2 square root 9, and then that's the 6th. So what happens when you know the answer, you write it in the wrong spot. All right. Well, similar to the normal line of the plane, you recall that a line that goes through a point x naught, y naught, z naught. I'm going off the edge. We're going to move this. With direction ABC, we wrote gave us the normal line. This replaced with df dx, df dy, df dz. It gave us to the first one, if the surface is f of x, y, z equals c, the normal line was x equals x0 plus df dx times t, a parameter. So y equals y naught plus df dy t, z equals z naught plus df dz t, where these are taken at the point And in the first problem that we did, we had the gradient was minus 6, 9, 16. So we simply plug in, and the point was minus 3, 1, minus 2. So it's minus 3, 1, minus 2. We had the point. And we have the gradient of the point was minus 6, 9, 16. So we just plug all those numbers in and we get minus 3, 1, 2 here plus minus 6t plus 9t and this is minus 16 plus 16t. There's the normal line for the first problem. Perpendicular to the plane. You can see it's perpendicular immediately. Wait a minute. Yeah, because these are the components of the normal vector. Now the second case is if you have z equals f of x, y. Now what's the normal vector? The normal vector now was, if you look back at the work, was minus df dx I minus df dy j plus k. When we subtracted f over and took the gradient in similar form, this was the normal vector. And so now, this was the second case, the special case, I guess we call it. So if we want to write the normal line for this, we have to put it in like that. So for the second problem, we just write x equals, let's see, the point was 495 we calculated. And the f dx was a fourth. df dy was a sixth. So we write down immediately the equation of plane of the normal line from that. X equals, x0 was 4, y0 was 9, c0 was 5, and we just take the point coordinates plus t times the partial derivative. Minus partial with respect to x, minus partial with respect to y, 1. So this would be minus a fourth, minus a sixth, and plus 1. So there's the equation of the normal line. You just write down the usual parametric form for a line, x0 plus at, y0 plus bt, z0 plus ct. But for here, you put minus df dx, minus df dy, and 1 is the normal vector. And these are just the point coordinates. All right, well, there's one last problem in this section. It's the hardest of all, of course. Trying to find the tangent line to the intersection of surfaces. This is really just supposed to illustrate that actually you do a lot more than is apparent to the eye from what we've written down here. You want to know how to find tangent planes and normal lines, but then once you know how to do those, you can use them to find lots of other neat things. So here's the last problem. Another section. use this geometry to find, let's see how to put it here, parametric equation. I was gonna do a separate one here, but I'm gonna do your homework problem. To find parametric equations for the line tangent to the intersection of two surfaces x squared plus 4y squared plus z squared equals 9. And z equals x squared plus y squared. At the point of intersection, 1 minus 1, 2. What's neat about these problems in here too is they give you some things you can sketch, right? If you think about how does this one sketch, right? You rewrite it by dividing by 9 and get x squared over 3 squared plus y squared over 3 halves squared plus z squared over 3 squared. This equals 1. This is actually an ellipse. You just divide through by 9, ellipsoid, excuse me. You divide through by 9 to see it in the standard form. So I can sketch this. It has semi-axes, 3, 3 halves, and 3. So it comes out 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. Its cross sections are circles in the XZ plane, but they're only half as long in the Y direction. 1, 2, they come out to about here. So I've got this kind of a figure. With, let's just draw an equator instead. How about? So it's this ellipsoid here. And now you're going to intersect it with this figure here. Z equals x squared plus y squared. Maybe you remember this one is a circular paraboloid, right? Cross sections are circles if you put z equal a constant, x squared plus y squared equals a constant. Or it's a parabola if you put x or y equal a constant. Z equals a number plus y squared, or z equals a number plus x squared. So we have this circular paraboloid that now looks like this. And these intersect, you can kind of see what it looks like. It looks kind of like they're gonna, it almost looks like a circle, but it's not because this ellipsoid hasn't got circular cross sections. But there's some kind of cross section here. And there's the point on it somewhere, 1 minus 1, 2. It's about here somewhere. And there's a tangent line to where these intersect, right? The intersection in a curve of some sort. And what is the equation of that line? So you got to think a little geometry here. Let's see. Now this is where I think the visualization helps. Think when you want an equation of a line, what do you need? You need a point on the line and a direction vector. So how can I get that? Suppose I took the tangent plane to the ellipsoid. I would have a normal vector to it. And suppose I took the tangent plane to the circular paraboloid, I'd have a normal vector to it. So I call these N1 and N2. What direction is the tangent line? Well, it lies within both planes, right? The tangent line to these two curves has to lie within both planes, so it has to be perpendicular to both normal vectors. We can find a vector along the tangent line by taking N1 cross N2. So that's the trick, is to realize that the intersection curve has tangent vectors within both planes, so I can take the cross product of the normal vectors here. All right, so let's say the normal of the first plane, N1. We don't even have to write the equation for the plane, right? We just need the normal vector this time. It's just gotten by taking the gradient at the point. Gradient of, if I call this F1, and call this one F2, function, not this side, F2. So it's F2 of xy equals, oops, oh, I write this a whole different form. I rewrite this one as x squared plus 4y squared plus z squared minus 9.
Can you move your camera so we can see?
Yeah, thank you. I have to rewrite this. I'll write this as f of x, y, z equals 0, and then I can call this function f1 using the first strategy for tangent plane and normal line. And then I'll rewrite this one as z minus x squared minus y squared equals 0, and call this function equal a constant f2. The reason I do that is it's harder to solve for z in this one. Otherwise, I could use the second strategy to get normal vectors. And now, the normal to equation 2, you just take the gradient at the point, which is 1 minus 1, 2. So what's the gradient to this one? I take the z dx, partial of this function with respect to x is minus 2x at the point I plus partial with respect to y is minus 2y, so it's minus 2y at the point j. So it's df dx I plus minus df dx I minus df dy j, and then plus 1k. I partial with respect to z is 1. And so I get, let's see, minus 2i plus 2j plus k. There's a normal to the second thing, the circular paraboloid. This one, similarly, I'll say, what's the normal to this function? It's df dx. Right, it's this one, df1 dxi plus df1 dyj plus df1 dz k. Looks like 2xi plus 8yj plus 2zk, and then I need it at the point. So at the point 1 minus 1, 2, up to 3 points. 1 minus 1, 2. 2 times 1 is 2i. Minus 1 gives you minus 8j plus 2z would be plus 4k. This would be the at the point 1 minus 1, 2. So here's n1, here's n2, and we just got to take their cross product now to get a vector that's perpendicular to both, and that'll be the tangent direction. Need to erase this in a second. So I'll take a vector v naught. It's their cross product. You can take the cross product in either order. Let's make the normal point in the opposite direction. It'll still be tangent. 2 minus 8, 4. With minus 2, 2, 1. And the cross product, right, is 2 times 3 minus 8 times 1 minus 3 times 2 minus 4 times 2 minus 8 minus 8 more is minus 16. Then I'll take 3, 1 is 4 times minus 2 minus 1, 3 is minus 2 times 1. That's minus 8 minus 2 is minus 10. And then 1, 2, just following, doing the fast cross product here, 2 times 2 minus 8 times minus 2. So 4 minus 16 is minus 12. A lot of calculations. Let's see if that looks perpendicular. This is, I can pull a factor of 4 out. It's 4 times minus 4, oh no, it's 2 times. Minus 8, minus 5, minus 6. Actually, I pull minus 2 out. Minus 2 times 8, 5, 6. So this is a normal vector. Also, you take the minus 2 out, that's a normal vector too. So we can call this, not the normal. This is the direction vector from the line. We can call this a direction vector as well as minus 2 times that. And now we can simply say x equals x0 plus at, y equals y0 plus bt, z equals z0 plus ct is the equation for the line, where this is a, b, and c, the direction of the line, and the point, lost it, was 1 minus 1, 2. Make sure this is right. Sometimes you get the cross product wrong.
Where'd that 22 come from?
22?
On the second line in front of you.
Oh, it's 2 times 2, sorry. There's a dot that doesn't show up very well up there. It came from this times this, minus this times this. So to calculate the cross product, the third component, I take first times second minus second times first. All right, so there's how you do it. I think that looks like it came out right. Minus 16 plus 10. Yeah, so this looks right. And the point's right, so we're good. Well, that's, yeah, hope I didn't run over time here. I was running close to the end of now. We've got a short extra credit quiz. It's just one problem on there, so I'll give you 15 minutes from when you get it in about 1 minute. Let me give the homework out first, so we don't miss that. There it is, 13.7. Can you see this part of the board? 13.7. 3 and 5 are the first type of tangent plane and normal line. 9 and 11 are the second type of tangent, the special case of tangent plane and normal line. And then 29 is the one we just did. I'll try those for next week and see if you have any questions. We did the last one. Hopefully that won't be a question. Turn this off.